All right. Good morning, everyone. My name is Guillaume, and today I'm going to talk to you about a new feature of Scala.3, which is called polymorphic function types, and how it works, and why you will ever want to use this, which turns out it's not most of the time, so you don't have to care too much about this talk, but it's still fun to talk about. So just briefly about me, I did my PhD at EPFL, where I worked on Scala.3, then I worked at the Scala Center, and recently, just last week, I joined a company called Martres that does interconnects for system on chips, which is like connections between CPUs and RAMs and other stuff. And if you're interested in working on the domain-specific languages in Scala.3 for hardware design, talk to me because we're hiring. Briefly, I will first tell you the difference between methods and functions, because it turns out that's going to be important to understand the point of this talk, and then show you how we actually handle polymorphism, and then talk about how this is implemented in the compiler, then give you some examples and show you how this will improve in the future. So what's a method first? So a method is always a member of some scope. Like it can be a class, an object, or a local block, and it's declared using def. So here, like we have a method that takes an int and gives you back a string by calling the toString. And a method is different from a function because functions are values. So what's a value? A value is always an instance of some type, and the type tells you what you can do with the value. In particular, function values are instances of function type. So here, f is a function value because its type is the function type int toString. But int toString itself is not actually magic. It is equivalent to function1 of int string, where function1 is defined as a trait that has a single method apply, single abstract method apply that takes the first type parameters of function1 and returns the value of the second type parameter of function1. And why is this important? Because in Scala, if you have something which is a value and you try to call, pass some arguments to it, like f of 1, it gets expanded to f.apply of 1. So this apply method is really the key to functions acting in the way we want. And the last concept that's important here is lambdas, because making an instance of function1 by hand would be annoying. So instead, we have this nice arrow syntax where you can write x goes to x plus 1. And this is equivalent to making an anonymous instance of function1, which itself is equivalent to making a class that extends function1 and that defines the apply method. So the difference between methods and value might still be very abstract because most of the time we don't have to think about this. And the reason we don't is because if you have a method and you try to use it as a value, so you have a method reference here, inc, and you try to pass it as an argument to map, then the compiler automatically does a conversion where it wraps your method reference into a lambda. Which, incidentally, this is called eta expansion because of lambda calculus, but the name isn't super important. But that's why most of the time we don't have to care about the distinction between these things. So, we just saw two different ways of basically writing code. Like you can have a method that takes a value, returns a value, or you can have a function that does essentially the same thing. So here, the method takes an int, returns a list of int, and the implementation calls the list constructor, so it creates a single element list. But both of these examples are monomorphic, which means there is no type parameters involved, right? We know, but in Scala, methods can have type parameters. They can be polymorphic. So I could write a method m that for any type t takes a value of type t and gives me back a list of t. But what if I want to do this at the function level? There is no direct equivalent, right? So if we wanted to invent this equivalent of polymorphic methods for functions, what will it look like? So probably it's something, we know that there's going to be a type, and there's going to be values of this type. And it's going to, here we want to call list of x, so there's going to be list of x somewhere in our implementation. So the only thing that's really important about the type of f is that it needs to have an apply method, because if I write like f and I pass it an int and 1, that should give me back list of 1. And the way this is going to work is that the compiler is going to, again, insert an apply method, an apply call. So whatever type we use here needs to be an apply, contains an apply, which essentially should have the same type as the method we started with. So just for this specific example, we could do this by hand. We can make a trait with an apply method of a correct form, and then we can make an instance of that trait. But that will be a lot of boilerplates if we wanted to do this for every possible method we want to wrap into a function. So instead, we want something more generic, like function1 for functions. So, and we want a nicer syntax too. So here, we could imagine a syntax like this, where, okay, I write f and I write a lambda from x to list of x, and its type will be t to list of t. But there's something wrong here, right? Because here we declare t and then we use it, but here t is not defined, so this is like not well typed, right? So we need a syntax that lets us define type parameters. So the syntax we actually ended up with, and there are some debates about this, is t as a type parameter is wrapped into brackets. And so a polymorphic function then takes a type t, a value that refers to t, and it gives you back something else. And the polymorphic lambda is symmetrical. So okay, I said that this stuff exists, and I'm going to show you in a minute how this works under the hood, but just to give you an example to motivate this is actually used in the Scala standard library as of Scala 3, because all tuples have a map method now. And the details are not super important, but like the idea is that because tuples are heterogeneous, like every element in a tuple can have a different type, you can't have the f you pass to your map can't be monomorphic. It has to work for every possible type that might be in your tuple. So the way it works is that it takes a polymorphic method, a function that takes a t, a value of type t, and gives you back an f of t. So you can use that to do various kind of wrappings. For example, if I have a tuple of int string, and I want to convert that into a tuple of list int list string, I can call map on my tuple and pass it a polymorphic function that does the wrapping. So to recap, we've got functions from terms to terms that we're very familiar with. And now we also have functions from types to terms, because f here takes a type t and gives us back a term. So if I pass int here, then I get back a function int to list of int. We also have functions from types to types in Scala, although they're somewhat limited. Like here, I can write type f of t equals list of t, right? And what that means is that I can put a type as input here, and I get back a type. And in Scala 3, we also have this type lambda syntax, which is easy to confuse with the polymorphic function syntax. But we had to make it slightly different to avoid ambiguities. But basically, this one takes a type, gives you back a type, in this text, a type gives you back a term, which is a function. And yeah, we don't have functions from terms to types in Scala so far. That will be dependent types. Okay, so let's go deeper now. So I already showed you how a function from int to list of int is just a function1 int list of int, where function1 is a trait. But now, if I have a polymorphic function, how do I represent this in the Scala type system? Like, we would add polymorphic function as a first class concept in the Scala type system, but if we'd prefer to reuse existing concepts if we can. So here's the first attempt. So here's my simple example I've been using so far of a function that takes a t and returns a list of t. And because this function has one parameter, one term parameter, one type parameter, I'd like to do something equivalent to function1. So let's define a trait polyfunction1. So right off the bat, this is already more complicated than the regular function1 because the parameter and results can depend on t. So in the implementation here for f, the parameter just takes t and gives me back t, and this one takes t and gives me back list of t. So this isn't too bad, but this isn't good enough because we might try also to bound t. So here, I haven't shown the syntax so far, but a polymorphic function, like a polymorphic method, the type parameters can have upper and lower bounds. So I can say that my t need to be a subtype of any ref. And so now my polyfunction1 traits also needs to take this bound into account. And now it gets pretty hairy and complicated. And we haven't even talked about multiple type parameters and multiple temp parameters. And so it gets like, clearly we need something different. I see Nicola having like huge eyes. So, so yeah, the idea is going to be to piggyback on another feature present in Scala, which is fairly obscure, which is like the structural typing support. So in Scala, you usually define methods inside classes or traits, but it's also possible to have methods defined directly in the type signatures as refinements. And this has some limited use cases. So here, like, foo is not defined inside selecta, but it's just defined in the type. But I can still call it here. And the idea is that while for our polymorphic functions, we only really care about the fact that there's an apply method of a correct type, but we don't really care about which traits or classes it implements, because we only want to call this apply in the end, no matter where it's defined. So the translation we end up with is that a polymorphic function becomes a refinement of an empty trait polyfunction, which is magic in the compiler. And this empty trait has a refinement which defines the apply method of exactly the type we want. So instead of defining a million traits for every possible polyfunction, we have one empty trait, and then we, in the type, in the desugaring, we add the method directly that tells us how we can use this function type. And so yeah, if we add an upper bound here, then we just add it in the desugaring. There's nothing special going on. So that's part of the battle. Now we've convinced the Scala type system that we have a polymorphic function, but in the end we do want to run our code and not just type check it, usually. So we'd like to compile this to Java bytecode and also to other platforms, but it turns out that what we do for Java bytecode usually can then be reused for other platforms. So because we always end up doing the same kind of steps. So in particular, when we're compiling to Java bytecode, we need to do type erasure, because Java bytecode is a bit like Java 1.0. There's no generics, there's classes, there's methods, but every time you have a generic, you have to remove it and replace it by its upper bound. So here, T is upper bounded by any. There's no any on the JVM, but the top type is object, so we end up with object. and traits become interfaces. And yeah, here function 1 of string to list of string becomes function 1. And then at use sites, we need to insert a bunch of casts that the compiler knows is correct, but the JVM doesn't. So this is how we communicate to the JVM information about generics that the type system knows is correct. So this is for regular functions, but now what about polymorphic functions? So here we have a polymorphic function that takes a value of type t and returns a list of t. And really, we could compile this in any way we want because we are not really bound by Java compatibility, because who's going to call our polymorphic functions from Java? But we do care about being efficient, which usually means you want some class or interface with a method. Like, you don't want to use reflection, you don't want to use a very complicated scheme, like simple is better. And so the idea is, we already know how to compile monomorphic functions. So we can take our polymorphic function and we can drop the type parameters. And so this thing then is very much like function 1. So let's compile it to function 1. And that's pretty much how polymorphic functions are implemented in the compiler. So yeah, for polymorphic function with n term arguments is erased like a monomorphic function with the same number of term arguments, no matter how many type parameters you have. Okay, so now I've shown you this weird feature, but you might want to worry about like, why would I ever need to use this? And again, usually you don't, but sometimes it's useful. So let's go through a few examples to convince you that this might be useful sometimes. And the examples will be quite elaborate again, because like most of the time you don't need this feature, so don't worry about that. So the first one is about generic programming. So I'm going to start with a type class. So here the type class defines a method to tell you if x is less than or equal to y. And so you could define instance for ints and say, x is less than or equal to y. I can use the built-in less than or equal on int, and same for string. Now, if I define my own case class with extra fields, so int and string, I would like the order on foo to be defined based on the order of its elements. Again, there's multiple ways to define order, but let's pretend we always want to do it this way because that's convenient for this example. So, you can do it by hand. You can say, okay, I'm going to summon the order of int and use it to compare my first field, then summon the order on string and use it to compare my second string. And summon in Scala 3, by the way, is the same as implicitly in Scala 2 with more precise typing. So this works, but imagine if I had like 10 fields or something in foo, then it would get very boring, right? So generic programming is about how to avoid that kind of boilerplate. And in particular, we can use shapeless free, which defines a product instances type class, which is going to be helpful here because, So product instances define a FODLEF2 method, and it takes as argument a type class and a class, so here order of foo, and basically it lets us iterate over all the elements inside foo, so A and B, and on top of giving us the elements, it gives us the corresponding type class instance. So we're going to have A and the order of int, then B and the order of string, and that's what our FODLEF will work on. So we start with a base value of true, because if we don't have any elements, we say, the empty case class is less than or equal to itself. And then here we have this rather long expression, but like the reason I'm showing you this example is just because this thing has to be polymorphic, because it's going to work with like we're traversing the elements of foo, and it can be of many different types. So here we get x1 and y1, which are the elements of x and y, and they might be int or it might be string. So here we get a t, And we could use any, but then what we do for the order. So instead we want something polymorphic, so we can say, okay, I have x of type t, y of type t, and then I have the order of t that lets us relate these things together. And the nice thing is about this is, well, usually if you're defining your own case classes, you wouldn't go to all this trouble. But if you're the author of the order type class, you can use the scalar-free type class derivation mechanism to define generic way for your users to derive your type class. And you can use this kind of mechanism inside your implementation to work with any kind of case class. So here, instead of foo, it could be anything, right? Okay, on to the second example of why polymorphic functions might be useful. So I'm going to show you a list implementation very similar to the Scala standard lists, except using the enum syntax, but that's just a detail. And the list only contains strings to keep things simple. It has a fold right method, which is the usual one. So fold right, if you recap, it's going to replace the empty element of the list by z here, and then it's going to rebuild the list by replacing every constructor by up here. And so this is sometimes useful. For example, if we want to append something at the end of the list, we can do that very nicely with a fold right, because we can, as the empty, instead of the end of the list, we can have one element list that represents the last element of a list. And then we can rebuild the list using the same constructor. So this works fine, right? And there's nothing that needs to be polymorphic here, but now I'm going to make the list itself more complicated by keeping track of the number of elements in the list in its type, which is going to make things slightly more complicated. So here I'm saying that a list has a parameter n that represents its size. An empty list has size 0, and a non-empty list has size m plus 1, where m is the size of its tail. So now, of course, when I append an extra element to a list of size n, I would like to get back a list of size n plus 1. But now my fold right function isn't going to work anymore, because fold right, like, it takes this b thing and the 0 of the fold right and the operation that combines the element and the result all have the same type b, but my last element of my list has size 1, because it's well, there's only one element, and my complete list has size n plus 1, so the types don't match anymore. So I need more generic fold right. Can you guess what it looks like? It took me a while, but so in this thing, I keep track of the size of my list as I fold over it. So the 0 element is b of 0. Because my list has n elements, the total is b of n, and then every time I combine an extra element, I increase the list by 1. So I go from b of m to b of m plus 1. And that's why up now needs to be polymorphic, because it has to work with any list of any possible sizes. And the way we're going to use this thing is a little bit devious, but we need b of 0 to be our new tail, our new last element of the list, which is of size 1. And we need b of n to be s list of n plus 1. So here we pass a type lambda that takes an x and gives me back an s list of x plus 1. And then the types work out. And yeah, by the way, this is relying on the scalar-free compile time.ops.int support that defines operations like type operation like plus on integer types. All right, last example. This one also weird, but in a different way, but also based on a real use case. So here I have, again, a type class. This one is very simple. It defines a method base that takes an element of type A, gives me back an A, so I can use it here. I have an A, and I create a.base, I get back an A. Now I'm going to make it a bit more complicated and define a second type class that extends base and adds two methods. One is called dangerous, the other is called compute and takes a callback. But this thing, I've decided I don't want to let the user call dangerous inside that callback. Like it's a requirement when you're calling this method, your callback is not allowed to call dangerous. So I can put it in the documentation, but ideally I'd like to put it in the type system so users don't accidentally do it. So how can I do that? So what I want to do essentially is hide some type information. So here, like if I have an A, then I can do anything that's defined on A inside, so I can call dangerous on it. But instead, I want to put some different types here to prevent this. So I'm going to define a compute safe method to show you the difference. And the first thing we could try is to do a method from any to A. And in a way, that solves the problem, because now I can't call A.dangerous anymore because A has type any, so I've hidden the information that this is a derived, but I've hidden too much information, in fact, right? Because now I cannot call A.base either. So let's try something different. So let's make it a polymorphic function. So it doesn't seem like that really solves the problem either, because I'm just saying, okay, f can take any type t, and then the callback goes from this t to t. But I still cannot call base inside my callback, for example. Like if I wanted to do a goes to a.base, I would like this to compile, but here my a, if it's polymorphic, then I don't have enough information to call a.base. So what's missing? There's a thing you want here, basically, and in scala.3 we have this other kind of function, which is a contextual functions, which is in the same way that in a method you can have an implicit or using parameter to pass a type class. In scala.3 you can have a contextual function that lets you pass a parameter implicitly. So here I'm saying that this callback will receive implicitly a base of t. And so now this thing is going to compile, because inside here, I only know that, well, assuming some type parameter here, but we could come back to this. Inside here, I want to, all I know about A is it's summoned on type T that has an instance of base. And so I can call A.base, but I cannot call A.dangerous on it. And if you wonder how in the hell I came up with this example, it turns out it comes from Katz effect. So please come find someone in the audience that works in Katz effect so they can tell you why this is useful. But essentially, they had to encode this manually because they didn't have polymorphic functions in Scala 2, right? Using a trait. Okay. So now that I've shown you some amazing examples, I'll show you how we can make this feature even better so it's easier to use, because as you've seen, the syntax is kind of annoying. There's always brackets and arrows and stuff you have to write everywhere. So can we make it simpler? And so first I'm going to talk about SIP49, Polymorphic Data Expansion by Quentin, who is also in the audience somewhere. And before I do that, I'm going to explain what a SIP is. So SIP is the Scala improvement process, which is how we add new stuff into the language. And the process, very roughly, is someone has an idea, they discuss it on the contributors forum, they write a specification of this idea, then the SIP committee, which is chaired by the Scala Center and has members from all over the Scala community, votes on whether this should be accepted as experimental, needs more work, or should be rejected. If it's accepted as experimental, then that's the go-ahead for someone to put some implementation on the compiler under some experimental mode, so people don't accidentally rely on it. And we gather more feedback. This might take several more cycles, and eventually, if everyone is happy, we vote on accepting the proposal as stable. So SIP 49, the SIP I'm talking about, is at the 4 stages, basically. And once something is stable, we actually mark it as stable in the compiler, so people can start using it in the next minor version. So the idea of SIP 49 is to take this concept of data expansion and generalize it for polymorphic functions and polymorphic methods. So here I have, again, a method that wraps a value inside a list, and I want to be able to take this method and use it as a method reference and pass it to map without having to manually add all this stuff around it. And so the polymorphic data expansion, as specified, the way it works is you realize that this thing is polymorphic, and map takes something polymorphic, and then you add term and types parameters, and you apply them in the exact order they were declared. So short and simple. And so we worked on implementing this, but then at some point I felt like this wasn't satisfying enough of a solution, which brings me to idea 2. But just with an example of why this isn't satisfying enough, it's like, this means this isn't enough to do, like we can do map of list.apply because apply is a polymorphic method, but we can't do map of list underscore, which is the same as map x goes to list of x, because that's a lambda, that's not a method reference. And so it's just a monomorphic method reference where a polymorphic one is expected. In the same way, we can't either do map of underscore to string. So if we wanted this kind of stuff to work, what would we need to do? So the idea I came up with, and this isn't something that's in the compiler yet. I made a PR about it, and I need to make a SIP, and I talk about it now, so to gather feedback from people, like part of this process, right? Is to have a concept of type parameter cross inference. So if I have an expected type, which is a polymorphic function, and I pass a lambda, which is not polymorphic, so it just x could be anything and goes to string. So right now this does not compile. And the idea is, well, if the number of term parameters here is the same, so here there's one, I could just add a type parameter clause that matches the one in the expected type. And then the usual type inference can take care of saying that, oh, this one is T. So this is fun because it relies on the fact that I'm not writing a type here, because I cannot write x colon T here, because T is not in scope, but I can say, well, it's some x. And then once the compiler has added this part, then the compiler can say, well, this x must be a T. So that's it, that's the idea. But what's interesting about this is once you have that, then you don't really need polymorphic data expansion anymore. You can use regular data expansion combined with this feature, and I'll go for an example to show you what I mean. Because, again, I have this singleton thing here. And what happens now, already in the compiler, if I try to use a method and as a value is we do this data expansion just on terms. So we can do that. We can say, well, this method takes one term parameter x. So I can say, well, this is a lambda from x to singleton of x. And now the type parameter clause in France I just showed can kick in and add the type parameter clause. And now regular type inference can kick in and add the type of this thing. And now I still need to add a type parameter here. But that's also something that regular type inference can do. And so in this particular example, this ends up being exactly equivalent to polymorphic eta expansion. But it can also work in situations where the method I'm working with has a different number of type parameters than in the expected type. Because like here, I need to produce a value which takes 2 type parameters. And I can do that. And the compiler will happily infer the correct thing here. Whereas with polymorphic eta expansion, it would have tried to produce this polymorphic function with 1 type parameter, but could not be adapted to this polymorphic function with 2 type parameters. So yeah, let me know what you think, how confusing this is. I think it works out pretty well in practice and is more useful than confusing in VM, but we can discuss that. And then yeah, the last idea I want to discuss is a much simpler, more natural thing that's missing from the current implementation of polymorphic functions. If you ever use them, you've probably run into it actually. It's the lack of natural subtyping. So with regular function types, as you're familiar, the result type can vary. So here I have a function from any to int. I can pass it to something which expects a function from any to any. The result type is covariant because if I return an int, then I can use it as an any. And for the parameter, it's the other way around. Things vary contravariantly because if my function can take a value of type any, then it certainly can also take a value of type int. Polymorphic function types, as they're implemented right now, are completely invariant, which is basically an implementation detail. Whereas what we want is something that varies naturally based on what the function can accept or not. So in the same way that regular functions are covariant in their result type, I would like polymorphic functions to be covariant in their result type. So if I can return an option of t, I can return an option of I can return an any. And if I take a sec of t, I can also take a list of t. Now, what about the type parameters? Which order do you think they vary? So type parameters, well, they're also parameters. So just like this thing here, it's going to vary covariantly. And if you work for an example, you can convince yourself that it has to be this way. We've added subtleties that you can also have a lower bound here. I could say t supertype of null, and then the variance will flip again. But we rarely use lower bounds, especially in function types, so it doesn't matter too much. But yeah, so this has been prototyped too, but we also need a separate zip since it's also a language change, but hopefully a non-controversial one. So that's it for this talk. Thank you very much for your attention. I've listed a few resources here, the slides for this talk, the Scala Free Compare Academy channel on YouTube, where there's a bunch of talks on compiler internals, the Scala contributors thread on the Scala Discord, where you can chat with other developers, and we're very open to helping new people. We organize live coding pair programming sessions online from time to time to work on the compiler and other projects. And we have also a physical Scala Spree this Friday in Madrid, where you can come work on the compiler, and also other open source projects. In fact, any open source Scala maintainer is welcome to come and help people work on their project. So please consider coming. Thank you very much.